Neutralization reactions are a type of acid and base reactions. They're kind of like the Arrhenius that we did when we explained that definition. Water and salt are formed when you react an acid and a base. So when you are doing a neutralization, this word goes right here. Neutralization is when you have an acid and a base, and it produces water and salt. And that is the basic formula down here at the bottom. But remember, when I'm talking about salt, I'm not just talking about NaCl, which is table salt, which is what you're used to thinking of. What trips people up on a test is it asks them a question about which one is the salt, and they're like, there's no NaCl in this formula, because it's a whole class of compounds. It's actually a class of ionic compounds, in which comes the cation, which is positive, and the anion, the negative part, comes from the acid. Okay, so it should be fairly easy to pick out which one's the salt, because it's a product and it's not water, and you know what water looks like. Okay, when you have a neutralization reaction, when you're having a strong acid and it is reacting with a strong base, it will actually produce a salt that is neutral. So if you had salt water, which was just salt and water added to it, regardless of what it was, it'd be neutral. Okay, and that's because the strong acid and the strong base neutralize each other. Okay, so that is a neutralization reaction. Here are two examples of neutralization. First is the classic example, which actually makes, and sometimes when we write it like that, but it's really H2O. But we write it like that so you can see that that H and that NOH come from the acid and the base. And so that's how we get that. But it's the same thing as H2O. We just write it as HOH so you can kind of see how it got there from the previous things. And of course, this would be our salt. If we're looking at this one, we have sulfuric acid and calcium hydroxide. This would be our salt in this case, because obviously that's water. Okay? So when you see an acid-base neutralization reaction and it asks you about the salt, pick the thing that's not water. That's basically it. Okay? Even if it's not NaCl. Okay? You could even have, you could say hydrogen bromide, which is a strong acid, plus potassium hydroxide, which is a strong base. In this case, you'd get KBr plus water. And so that would be your salt right there. Okay? So now we can go to titrations, because titrations utilize that neutralization reaction. This word goes in this blank, titration. And it's when we have a known concentration of one of them, we can find the unknown concentration of the other one. So in other words, if I know the concentration of my acid, I can do this technique of titration and I can figure out what my concentration of the base is, which is what you'll be doing in your lab tomorrow. In the burette, you have a known concentration of acid. There's 3 unknowns. Each group will be assigned a different one, and you're going to do the titration to calculate what's the concentration of the base that you don't know. And that's what we'll be doing. And it utilizes something called indicators, which are going to be in the flipped lesson you watch. But basically, indicators are compounds that change colors based on the pH. Okay? And we're going to be using an indicator called bromethymol blue, which will be blue in the presence of a base. And when you titrate it and the solution goes from a base to an acid, it turns yellow. Okay? But we're going to be looking for a sweet spot of green in the middle, which is when it's exactly neutral. It's kind of hard to get. So if you get green, you're doing really well. Most people overshoot it, especially because you've never done titrations before. Best way to try to get green is when you get close to that endpoint, you go super slow, 1 drop at a time, because literally 1 drop can make the difference because it's very, very sensitive. And so I will show you the technique tomorrow before you do it, and then you'll try it on your own. Okay? The titrant is the known concentration. It's going to usually be in the burette. Okay? And that is, you'll see a picture of that in a second. Anybody see in the lab the last day or two where they've got those long tubes set up? Those are called burettes. And burettes are very precise, a volume delivery system. They're very precise in how much volume they deliver, like 0.01. You're going to estimate to 0.01. So they're really, really precise. Way more precise than a beaker, way more precise than a graduated cylinder and things that we've been using. Okay? The end point is the point at which the color changes, and that's how you know to stop the titration. When you reach the color endpoint you're looking for, you stop. Okay? And it is seen by color change. Phenolphthalein is an example that is colorless in the presence of an acid, and then when the pH turns to a base, it turns pink. It's a really pretty pink, actually. And like I said, we're going to be using brome thymol blue. And if you get to the color of urine, you went too far, because it's supposed to be green, not yellow. And it pretty much is the color of urine. The equivalence point is different than the endpoint. It's actually the point at which you have exactly the same amount of moles of hydrogen and hydroxide, okay? But unless you're doing a titration with the pH meter, you can't see that. At the equivalence point, it might remain no color change because you're exactly equal. But you get that one drop more of either acid or base, that's when that color change happens. So they're not exactly the same, but for calculation purposes, they're close enough for government work, because the amount of difference it's going to make in your molarity is very minuscule. Okay, so endpoints are just a much quicker, easier way to do it. These are the steps involved in a titration. And of course, we'll go through this when we go through the lab. You have to know how much unknown, so it's going to be very important tomorrow to measure the volume of the base exactly on the milliliter mark. Don't just say, oh, it was 10. No, you need to make sure it's 10, because if it's 9.8, you need to record that it was 9.8, not 10, because that makes a difference in your calculation. You're going to have to add the indicator. So if you don't start the titration tomorrow and your solution is blue, then you're not starting correctly, because you'll never see a color change if you don't add the indicator. When you're using the burette, I'll show you in a second how you read it, but that is your titrant. So you're in the lab, you're given the concentration, and you'll have to accurately measure how much volume of that you used, so then you can do the calculation. Okay? So this is what your basic setup is going to look like. So the way that a burette is marked is 0 is marked at the top, and down here at the bottom it's marked 50, because they're 50 milliliter burettes. Obviously, if you have a 25 milliliter or 100 milliliter, it's 0 to whatever you have. But it's kind of confusing because it starts at 0. Normally when we pour liquid, we read from the bottom up. You're going to be reading from the top down. Okay? So in your lab, it's going to ask you to record the initial reading and the final reading, and it's going to be set up like this. Okay? Let's say you walk up and it's like right here, so it's not exactly on 0. You're going to read that as, let's say it's 2.3 milliliters. Okay? Meaning 2.3 milliliters is gone from the burette. So we do our titration and we get done and it ends up right here. Okay, so we end here. Then we read that and we say, oh, that's about 15.7. So we would write down 15.7. Then to get how much we used, we do a subtraction problem. So it would be 13.4 milliliters used. And then that would be the number we used in our calculation. Okay? You're going to do 2 titrations. Okay? So the second titration, your initial volume would actually be the final one you just ended, right? Because you're not going to refill between, because they hold 50 milliliters. And so the second titration, you would use the 15.7 as your initial for your second titration. Does that make sense? Okay. Because that's the hardest part, is people not reading the burettes right. Okay? And then you'll do your second titration, and then we'll do the calculations. Okay? And what color are we looking for tomorrow?
Green.
Green, but what do we mostly get?
Yellow.
Yellow. Yeah, it happens. Especially if you go too fast. So when we're doing strong acid, strong base titrations, which is the only thing we'll do in here, because it's a whole different class of calculations if you're doing weak acids and weak bases, because they don't ionize completely like strong do. I'm going to give you a formula. You can do it with stoichiometry. It's probably the last time I'm using the formula, because the other teachers, they like the stoichiometry way better, but I've already started giving this out, and so I've got to be consistent. It works. You get the same answer, but you have to understand the difference in the formula than the dilution formula. So the formula for this is MAVA NA is equal to MBVB NB. Okay? What do you think the A stands for?
Acid.
B?
Base.
Okay, what's M? Molarity. Remember, we're talking concentrations, we're talking molarity. So M is molarity.
Volume.
That's right. V is volume. Here is the difference, are these right here that you got to worry about. Okay? Na is the number of moles of hydrogen in your acid.
What number of
Moles of hydrogen in your acid. N is your moles of hydroxide in your base. Okay? You have to include that in there, even if it's 1, and you have to include the units on there so you can see how it works. Because when we have this is the simple reaction of what's going on in a titration. Because the salt is aqueous, it stays dissolved. You're actually forming liquid water. That is the actual reaction that's happening. And so we have a hydrogen reacting with a hydroxide that forms water. So that's why we can use this formula. So let's do an example problem. And I have stars right here because in your notes, I don't know what I did. It's wrong in your notes. So fix the second side. Okay? So before we ever start, I want you to figure out what Na and Nb are so that you can put them in the formula correctly. So HCl has how many hydrogens in the formula? 1. So Na would be 1 mole of hydrogen. Nb, how many hydroxides do I have in the base? 2. So that would be 2 moles of hydroxide. So now we go and read our problem. I know that I have 20 milliliters of magnesium hydroxide at that molarity. So that would be my titrant. Yes?
On one side it has HCl and on the other side it has Cl2. Where does the other one come from?
If you look at your formula, I actually wrote yours wrong. I wrote NaCl. I didn't balance it.
Oh,
Yeah, I haven't balanced it. When I use this formula, I don't necessarily have to balance my equation.
okay.
I just have to...
Confused where it
Yeah, no, if I was doing it stoichiometrically, I would balance my equation, use mole ratio just like I did for stoichiometry. But I know how much y'all love stoichiometry. I mean, I can go back to that way if you want.
Sucks. I still don't know how to do it.
Okay. All right, so NB in this case, because it is 2 hydroxides, it's going to be 2 moles of hydroxide. So we have 20 mils of base, and we know the molarity, so that's actually our titrant. And then HCl is our unknown, and we know that we use 10 milliliters of it. So we're going to be solving for molarity of the acid. So we're going to take that formula, and we're going to rearrange to solve for molarity of acid. Okay? Now we just plug everything in. So the molarity of the base was 0.0050 molarity times our volume. Because we're going to have volume on the top and the bottom, we can actually leave it in milliliters because they're going to cancel out. And then NB was 2 moles of hydroxide. Here's where I'm telling you, you have to show your moles of hydroxide because you're essentially showing your mole ratio of what's reacting. Okay? So then you have 10 milliliters of acid that it used, and then 1 mole of hydrogen. So we're showing that for this particular reaction, it takes 2 moles of hydroxide and 1 mole of hydrogen that react. So now we plug that in our calculator, milliliters cancel out, and then moles cancel out. And then I think that comes out to 0.02, but I don't remember for sure. Does it? Okay. So we need 2 significant figures because everything in there is 2, so we would write that as 0.020 molar HCl. So that would be our unknown. Now tomorrow when you do your titration, it is sodium hydroxide and HCl, so it's a 1-to-1 ratio. But when you show your calculations, you still need to write 1 mole of hydroxide, 1 mole of hydrogen, and show that you know what's reacting. Okay, so that's how you'll do the calculations tomorrow. You'll do 2 trials. If your volumes that you titrated are roughly fairly close to each other, you can be done. But if you get way off, like let's say one time you use 5 mils and the next time you use 7 mils, that's way off. You would need to do a third trial to see which one is closer and then throw out that outlier. Okay? Any questions on that? Okay. Oh, you have a question?
None of us